Good morning everyone. Myself I am Chaitanya. I am posted as a Deputy Director at National Water Academy, Central Water Commission, Pune. Um, Today we will be working with the raster data using Google Earth Engine. Yesterday we have seen introduction to Google Earth Engine code editor, some basics of JavaScript, data types, and Earth Engine objects and methods. We have seen that image collection, feature collection are the common Earth Engine object classes, and a specific instance of any object class is an object, Earth Engine object. Image and features are the most fundamental geographic data structures in Earth Engine. Image is the fundamental raster data type in Earth Engine, whereas feature is the fundamental vector data type in Earth Engine. Image is composed of bands and a dictionary of properties, whereas feature is composed of geometry and a dictionary of properties, similar to attribute a table of shape files in case of in GIS parlance. A stack of images is handled by an image collection object class, whereas a collection of features is handled by a feature collection object class. Yesterday we have seen that by printing out information onto the console, we can get information about the object, image object. We can get you can also get metadata, and we can also use console for debugging purpose. Um, by adding the map layer to the map canvas area, we can visualize the geographic data. Now today we will before going with raster data analysis to Google Earth Engine, I will be showing a few help topics in code editor. On the top uh, uh, right hand side corner there is a question mark which points to the help user guide, which is very extensive, and you can use you can go through it whenever any help is needed. And there are developers discussion for our group at the other support options, question and answer site, then general shortcuts for usage in the scripts, then a feature tool for Earth Engine code editor. And in the script manager, yesterday we have seen that there are examples for many object image for many Earth Engine object classes which you can make use. Then in the search bar is used for search. We have seen that any data set can be you can search for any data set using the search box on the top. Now to view all the data sets available in the data catalog, at one place there is you can visit this URL earthengine.google.com, and by clicking this tab of data sets, you can have a look at the all the data sets which are available on the Google Earth Engine public data catalog. You can and each of the data set has a brief description, and you can even browse the data set available data sets through tags, and you can search for them. And all major satellite imagery series like Landsat, MODIS, Sentinel, they have separate sections. Then you can also have a look at frequently asked questions FAQs, then time-lapse videos which are generated using Landsat series, which is the Landsat satellite imagery series is available for last 35 to 40 more than 40 years, and major land use land cover changes due to natural reasons or due to anthropogenic reasons. You can visualize them using the series of Landsat data, satellite imagery and then there are case studies which made use of Google Earth Engine. There are various applications have been built on the basis of making use of Google Earth Engine. You can have a look. Then coming to the today's topic, we will make use of the same repository which was shared yesterday. We will start with script 02, working with the single band image. In this script, working with the single band image, we will be working with two data sets, SRTM DEM, digital elevation model. You must be familiar with it, and then CHIRPS, precipitation, daily precipitation data. Both are single band image. The SRTM is a image, DM is an image, and CHIRPS is a image collection. You can search for any data set using this search box, and SRTM, you can click on the the data set to get a brief description of the data set, the bands which are available. In this specific case, it is a single image, single band data set. Elevation is the only band. Then you can have a look at the availability, temporal availability of data set, the time period. Now in this case, the data was collected once in 2000, and since then it has it is under it has been processed many times, and many versions have come to fill data voids, and then the data set provider is given here, and this is important, the ID of the image, which can be used in our script by using this ee.image connector. We can call it into our script, and we can make use of the data set. Alternately, we can import it by clicking this button, which will create a variable in the import section on the top of the script. I have already done that, and a variable has been created importing the data set, and have renamed the variable as SRTM for ease of use. Now we will start working with it. I will comment out the script, and I will go in a sequential manner. Once you have imported the data set to the import section, or you have declared it in the script by assigning the data set to an variable through Earth Engine image connector, we can start using that data set. Now we have to define a region of interest. Here I will define a point as a region of interest. I will search I'm in Pune. I'm looking at Pune region, and in the outskirts of Pune. This is the location of the office building of National Water Academy. Now using the inspector tab, you can get the coordinates of this point, the longitude and latitude, and you can create a you can, by using interactive tool geometry tools, you can create a point layer, and it will automatically generate a import a variable in the import section. You can rename it as ROI, region of interest, which is a point feature, and we can make use of it in our script. Now if you want the map canvas area to be centered at your point of at your region of interest, you can make use of the method map dot set center. It centers the map view at the given coordinates with the given zoom level. It is a method available it is a method available under the map object class. um, so I can so in code editor there is a shortcut, or you need not remember the whole all the methods. You can while using the Earth Engine Google Code Editor frequently, you will get to know the important functions, and you will be having some idea about the keywords. Therefore, you can search those keywords in the docs under the in this search box under the docs. Or there is one way is you can there is a if you press control, there is a short key. By pressing control and plus space, it will sorry control plus space, it will show options of all the methods which are available with map object class. map.set, we are looking for this method, and you can just give these coordinates as the input, say 73.8 comma 18.5, and the zoom level, which varies from 1 to 24. I'm giving a zoom level of 12, and I will execute it. It will center the map canvas area at that coordinate and given at the given zoom level. Now yesterday we have seen that we can import our own data sets, whether a raster image or a shapefile into assets, private assets, and you can make use of it in your analysis. Now I have uploaded a shapefile of Pune district by using this upload option. Here you can upload images, and you can upload shape files, CSV files, and then it will create a task, and after it will take some time, and once it gets uploaded, you can view it, and you can import it by clicking this import. It will be imported into the import section on the script, and you can make use of it in your script. I have done that. So I have named the variable as Pune district. So we have the asset, and I also in the settings I have made it a public. I have shared it with everyone, so it is public, and anyone even you also can use it in the script. You can run the script by making use of this asset which is which was uploaded by me. So there is another function method which is available with the map object class. One thing is, yesterday we have seen that these are all those object classes starting with EE Earth Engine object classes. They have a specific list of methods which are available, which you can use in your scripts, and there are some code editor specific methods under map, chart, export sections, which uh, don't come with the Earth Engine constructor, and they are specific to code editor for visualization purpose on the code editor. They don't communicate with the server, Google server. So and one there is one here we are make using of another method under the map object class, Earth Engine object class, which centers the Pune district, and again the same zoom level with a given zoom level. You can search it under the docs, and you can see what are the the syntax, what it does, and what are the parameters which are required, which of those parameters are compulsory, which are those are optional, and what it returns. You can have a look at the documentation here. So if and because I have given a zoom level of 8, um, I can increase the zoom level to 12. Then it shows the map canvas area with Pune district um, located the center of the map canvas area. Now how to add layer? It is again a function under map. You can search for it. You can add either raster layer or image or a vector. Here in this specific case, if I want to add the Pune district, the feature here, I can do that using this method map.addLayer, which again this adds an EE object, Earth Engine object, to the map as a layer. It can be a image, or it can be a feature, it can be a collection, anything. Then you can start typing and make use of control space, and then it auto completes the code. Then you can pass on the parameters. In this case, Pune district is the object, and you can give visualization parameters in the form of dictionary. For image, you can only give color. For features and feature connections, the only supported key is color, so you can give the color. You can execute it. It will show the feature, the asset which you have uploaded on the map canvas area. Then coming to our main the SRTM layer image. If these two lines are adding the SRTM layer onto the map canvas area, add image to the map panel as a layer, and we are only passing the object, image object. We are not passing other parameters. So let's execute it by uncommenting it and then running it. It will add SRTM layer on the map canvas area. You can increase the zoom. Since we are not passing other parameters like name of the layer, it is by default it is taking layer 1, it is giving names in the sequential order. Now in this layer 2 is SRTM DEM. Now the visualization is not proper because it is a all single band images. In Earth Engine, by default they display in grayscale, and the minimum value is assigned to black color and maximum value is assigned to white. In this, if we make use of inspector on this layer at any location, like at our region of interest, the you can get the elevation at any point, but you are unable to view the image because the that because in this case the range of the values, the elevation values, have been stretched as per the data type. Like the SRTM image, You can see the SRTM image. I will comment out and I will comment out and I will print SRTM image onto the console to see its metadata and see its properties. Now SRTM is a image. It is a image type. It has one band, and bands in object image objects listed are in the form of lists. Here the index of the first, there is only one band elevation with the index 0, and this elevation, the data type of it is signed integer. Means the value of the elevation uh, is stored in the signed int 16. That means the values of elevation here are stored uh, they are stretched along this range. That's why you are unable to visualize it. For those who are familiar with using GIS software, you must be aware that we can stretch these values for better visualization. I am doing the same thing for here. The value of elevation are ranging between 511 to 785 for this portion of the map canvas area which is visible. So I can apply it, so then you will be able to see the image, the DEM. Then we can also add other parameters in the map.addLayer method for better visualization of this data set. So here I am adding SRTM, the map object, the image object. Then I am passing the visualization parameters in the form of a dictionary, minimum value, elevation, around the range here. It varies from 511 to 785. I am giving a minimum value of 500 and maximum of 1200. Then we have to define a custom palette. Here it is defined in such a way in the within single quotations. You can give an input of comma separated values of color hex. You can either name the colors, or you can give it in the form of hexadecimal color code. Then what happens is, all those values of elevation which are equal to minimum value of 500 and below will be assigned, will be shown in the green color, and all those values which are which are above the maximum value will be assigned this color, all the pixels, and remaining in between it will undertake intermediate colors are linearly stretched. And if I run this script, and I am also giving the third parameter, which is the name of the layer. So here we have a new layer of SRTM. The layer is named. In this way we can improve the visualization of layers after adding them to the map canvas area. And you can inspect the values of elevation. This is a plain region, so you have elevation is less, it is around 200 to 100 meters, and then here we have Western Ghats and it gently slopes. You can inspect the values. So let's not spend more time on this. Let's move forward. And one more thing which will be useful for visualization purpose. We can also the color, while defining the colors are defined using the web standard CSS color value schemes, hexadecimal strings, which you can easily add on your own. You can visit this URL colorhexa.com. Let us say if I want to repeat the same thing by defining a custom palette of colors, I will comment this line out and I will define a new palette. You can also define the palette from this layer manager by adding the colors. Now I am because I want to um, introduce you to this easy way of adding hexadecimal strings. I am doing this. Now let us say if I want to range the values from, say, I can press any color, dark green. I want to assign lower values to dark green. You search for it, and this is the hexadecimal string uh, for dark green. You can just copy it and you can paste it here in the palette. Light green, yellow. So in this way you can define your own custom palette and have better visualization of images on the map canvas area. And I am executing it. If you zoom out, the range of the values will also change. You can again do the stretching, custom stretch, and then apply it for better visualization. So this so let's move forward. Then next we will see how to apply a computation to the image using Earth Engine object. Now we are defining a new variable slope here, and we are making use of specific method, Earth Engine method, which is available under Earth Engine terrain object class, which will calculate the slope from the input. It calculates the slope in degrees from a terrain DEM. So I am here what I am doing is I am applying a computation to the DEM image using an Earth Engine method, which is dot terrain dot slope, and we have to give the input of DEM, which will uh, compute the local gradient using connected neighbor. For each pixel it will compute the slope local gradient using the connected 4 neighbors of each pixel, and therefore the edge in the edge you there will be missing values because there won't be any neighbors on the edge in the so it returns an image. So this method will take SRTM as an input and it will calculate the slope, and I am adding the same layer using this method map.add_layer and naming it as slope, and I am giving the visualization parameters. I am not giving any color palette. I am only specifying the minimum and maximum value. This only by intuition. We can change these values upon inspecting the slope values. Let us run the script and let us inspect the values. I'm only keeping SRTM and slope layers on. So slope is a gray scale image, all black. The low slope values are in dark color, and bright color we have um, areas with higher slope. It is still getting generated. Okay. So it has computed a new image slope from the input of SRTM DEM, and it has generated this layer. Now if we want to calculate average slope for a region of interest, uh, let us define a new region of interest. Let us delete this point, and you making use of geometry tools. Let us define a polygon. Double click to close the polygon. Now it has imported a variable geometry with 5 vertices, the same polygon. You can rename it as variable as region of interest, and we can calculate the average slope for the region of interest using these lines. I'm uncommenting and defining a variable average slope, and using a reducer. We have a new method called reduce region under image, under ee.image, with this syntax, which this method applies a reducer to all pixels in a specific region. Here we are defining a specific region of interest, that is the polygon. And what this method does is, it will we have to give the type of reducer that we want to apply. We have to give the geometry, in this case the region of interest, and there are other parameters uh, which are optional. I have intentionally selected a small region of interest. I will tell you why we need to be careful. Let us execute this first. Here we are passing, yesterday we have towards the end of the presentation we have seen that the parameters for any method can be passed in the same sequence, or we can pass it in any order using a JavaScript object or dictionary. Here we are doing the same thing. We are applying the we want to apply the reduce region method to the slope image. We have generated the slope image here, and here we want to apply this reduce region uh, uh, on an image, and these are the parameters which we need to pass in. We are selectively passing on the parameters using in any order, using the name, like the name of the reducer. We want to calculate the average slope of the region, so I am passing the reducer ee dot reducer dot mean. This is a it calculates it returns a reduce it computes the weighted arithmetic mean. So I am specifying the reducer which will calculate the average values of all pixels in this region. I am specifying the geometry. uh, I am specifying the reducer. I am specifying the geometry which is essential, that is a region of interest which I have defined as a polygon. Then I am specifying the scale, which is also the I am taking the native image scale, that is 30 meters. The DM is also in the same also has the same resolution. uh, then rest of all are optional parameters, and then I am printing the average slope in the by passing two arguments, one string, and I am this method will calculate the average slope for this region, and it will print the average slope. If I execute this script in the console, you can see that it is printing this print statement is printing the value of the average slope for that region of interest in the form of an dictionary, one key, one value dictionary. So the average slope for that region of interest is 1.12. Now let us just play around. I can move this region of interest. You can just move this around. You can take this take to this region which has high areas of higher slope. Then if you run the script again, it will calculate the average slope for that region, which is 19.29 degrees, which is comparatively high. Similarly, if you take to the plain region, or if you it will generate a less average slope. So I think you understood the process. The main thing is we are making use of reducer. We are passing the parameters here as JavaScript object dictionary as single argument to this method. This is one way of applying. This method is being applied on this image slope, and we are passing the parameters in the form of a dictionary, and it is returning a dictionary of average slope, and we are printing it. Now what happens if we if I delete this region of interest, and if I create a big polygon using this interactive tool? Say if this is my region of interest, and if I try to execute the code, it gives an error saying that there are too many pixels in the region. Now in the one of the parameters here for the reduce region method is maximum pixels, which by default is 10 power 8 number of pixels. It is the maximum number of pixels which can be reduced for reduction purpose. So because it is exceeding this 10 power 8 pixels, you are getting an error. Now how to avoid this error? You have to we have to increase this number by specifying the maximum number of pixels as a you have to pass it as an argument here. You have to pass it as an argument of you can specify the number of pixels. You can increase the number to 10 power 10 or so. And there is one more parameter, best effort parameter. If the polygon would contain two, you can turn it on. You can by default it is false. If you specify it to be true, like say for this region polygon which I have which I have created on the map canvas area, I am passing the best effort argument. The parameter is best effort and the argument is true, otherwise by default it is false. It is an optional parameter. And then I am also specifying the max pixels. I am increasing it from the default value of 10 power 8 to 10 power 10. Say, then if I run the script, then it will not generate the error even if the maximum pixels are exceeded by 10 power 10, because I have turned this best effort to be true. What it does is, even if the polygon contains too many pixels at the given scale, it will compute and it will use a larger scale which would allow the operation to succeed. That is, the maximum pixels will not be exceeded by varying the scale. So I have got the value of slope for this big region of interest, which is 3.05, around 3.05. Okay, then let's move to the next data set, which is chirps daily precipitation. Now, how to calculate the rainfall statistics for a region of interest from the imported asset. Here I have I have imported the Pune district asset. Now I want to I will quickly read the code. Here what I am doing is, I have already imported chirps by searching for the data set in the search box, and have imported this chirps. You can read the description. It is again in the single band image, and I have imported it. I have created a variable in the name of chirps, which is an image collection. If I try to print chirps here, let us say I will print chirps, and I will comment out the rest of the code. So it is an image collection, and it is an image collection, but it has been aborted because again, whenever an image collection has more than 5,000 images, whenever, not just image collection, for any collection, if it has more than 5,000 elements, it will generate an error, because each image will have a lot of data properties associated with it, metadata. So after accumulating over data of over 5,000 elements, it will give an error. So it is better to filter the image collection. You need not, once you are importing chirps, means it is the data is itself is available from 1981 to December 2020. So this image collection has thousands and thousands of images right from 1981, not thousands, because it is a daily data. You will be having even in lakhs of images in this collection. So you have to filter out, if you want to do any analysis. Let us say you want to calculate annual rainfall for the year 2020 for a specific region of interest. Say let us fix the year as 2020, and let us fix the region of interest as the Pune district. So you have to filter the chirps data, we are doing the same thing here. We are filtering it by date. I am declaring a variable chirps filtered, and I am passing on the image collection chirps which I have imported here, and I am applying a filter date method. Now any method, you simply search in the docs, and it is under the, because it is an image collection, you see it under the image earth engine dot image collection object class. You read the description, you read what all are needed to be passed into the function method for execution, and what it returns. So here it takes start date and end date, and it will again return a collection. It means it will return a subset of the entire chips data is from 1981 to 2020. Now here we are only seeking a subset for the year 2020 by specifying the start date and end date in the form of strings in this fashion: year, month, date, year, month, and date, end date, start date and end date. So it will generate images, because it is only a number of images, because it is a daily data. The number of images would be only for 1 year would be only 365. Therefore this chips filtered is also a collection, image collection, which will have only 365 images, or depending upon whether the 2020, maybe it may be a leap year, there will be 366 images. So if we print, let us say we print this variable to the console, let us see what happens. I will comment out the rest and I will execute it. So it is an image collection. And how many images are there? There are 365 elements. There are 365 elements in this collection, because the end date is not inclusive. Whenever in this method, it will start with 1st January 2020, but the end date is not inclusive, means it will have images up to 30th December only. So for to even have the image for December 31st, you have to give the end date as 1st January 2021. Let us run it again. Now it has 366 elements. So all there are all images in this image collection are in the form of a list. Under features, there are 366 elements with starting from index 0 to index 365. So this is in this way you can use the print statement to see what is the how many elements are there, how many images are there in an image collection, what are the properties. You can also view their metadata, and likewise. So let us go forward, and let us so we have we have filtered the chirps daily data for the year 2020, and in here we have calculating the cumulative rainfall for the year. We are simply adding the rainfall of all the days by taking this as an input. The chirps filtered, that is the data for 2020, we are adding using the method dot sum. So it will calculate the on each pixel. What it will do is it will calculate the accumulation of rainfall on that pixel for all the 366 images. Then we are to visualize the total rainfall by adding a layer to the map panel. Let us see this now. Once after I will comment this. So till now we haven't filtered the image collection we have only filtered for the temporally we have done we have done only temporal applied only temporal filter. We haven't applied any spatial filter. So let us visualize the total accumulated rainfall by adding this total rainfall. What would be the type of this total rainfall? Because it is a sum of the image collection, it will be a single image with having each pixel having sum of the rainfall for 366 days. So it will be an image object. Then we are specifying the visualization parameters with the minimum value of 0 mm and maximum value of 3000 mm. And then palette we are giving two colors, white and blue. Let us run this script. It will it will add a layer of total rainfall to the map canvas area. Because we haven't done any spatial filtration, it will calculate for the entire map canvas area. So this is the total accumulated rainfall for the whole India. It will generate. Anyway, it will take time. Yeah, as expected, the you can see high rainfall in the west coast region and high rainfall all along the foothills of Himalayas and in the northeastern region. Okay, then let us calculate. Let us also filter the collection. No, it is now let us clip the area. This we have all, because we have already generated the total annual rainfall. We will clip the total annual rainfall for the Pune district using the function method, uh, clip method. So we are declaring a variable Pune total rainfall. Now this type of usage of phrases without any space, with change of word indicated by a capital letter is known as camel case. We use it in Earth Engine. Not much significant. Then let us so we are taking the total rainfall image and we are clipping it for Pune district. Pune district, we have declared it as a shape file. We have imported it and we are adding, then we are adding the this clipped image with the same visualization parameters which we have seen for the entire map canvas area. Now if I execute this, it will only add layer for Pune district. Because it see, it has clipped it for Pune district and adding the layer. I haven't named the layer. I can even give the some name to this layer, Pune annual rainfall. And if I execute it again, it will generate a layer Pune annual rainfall, and you can inspect the rainfall values at any pixel. It is annual rainfall. It increases as we go towards the Western Ghats. It is more than 2600 in this region, around 3000 region. So we have given reasonable values as max and min. We can do the stretch here, custom stretch it for percentage of the value. So the minimum value here is 726.27 in this district, and the maximum value is 3278.6. So annual rainfall varies from 726 mm to 3278 mm in Pune district. So then next let us calculate the average annual rainfall for the Pune district using this method of reduced region, which we have already used for calculation of mean slope, average slope. We are doing the same thing here. There are two ways to do it: passing on the parameters sequentially, or you can pass it as a single JavaScript object by in the form of uh, parameter argument key value pairs. So we are specifying, we are taking the total rainfall image, and then we are reducing it for this region, specifying that the region is Pune district. We are by applying the reducer ee.reducer.mean, and we are applying the scale as 5000. It is the native resolution of the CHIPS data, 0.5 degrees, 0.05 degree. uh, each cell is of 0.05 degrees, that is around 5 kilometers, which is 5000 meters. And then I am printing the return value. It returns a dictionary. So let us execute it and let us see what it prints. So it is printing the average precipitation value, which is 1347.198. Now what is this key value precipitation? Where from it is getting this key? I am not giving I am not providing, I am not passing it anywhere. This precipitation it is getting from the original CHIPS band description. If you see, CHIPS in the band is named precipitation. So by default it is taking the name of the band as the key, and the value is it is calculating for this region. It is calculating the average value. So the average rainfall, annual rainfall for the year 2020 for Pune district is using the CHIRPS daily rainfall data is 1347.198 mm. So this is how we make use of Earth Engine methods for single image objects. Now let us go to multiple band images. See. Next we will move to the next script, which is working with multi-band images. Now multi-band images. Now Landsat 8 is a multi-band image which we want to the Landsat 8 image collection. We will make use of it. We will so I have searched for this Landsat 8 collection, tier 1, tier top of the atmosphere reflectance image collection, with which has around 11, 12, 13 band no 12 bands. And the data set availability is it is available. Landsat 8 series satellite imagery are available since April 2013 to the current date, and the data set is provided by USGS, and this is the because it is an image collection, it has an Earth Engine image collection constructor, and this is the ID of that collection. So we have already imported it here, and we have named the variable as L8, and I have also defined a point of interest, region of interest as NWA near Pune. I have defined it, I have imported it using this geometry tool. Then here what we are doing is using we are printing the size of a Landsat image. Now if we are not importing in the import section, we have to declare it as variable L8 is equal is ee.image collection and then ID. But we have already imported it, there is no need for it, and so I have commented it out. And then let us print the size of this collection, image collection, by using this method image collection L8 dot size. I am printing it. Let us see what happens. Again, I think it will throw a error because no size it will anyway display. It will not print the whole collection, but it will specify the size. It is still computing because so it has around 11,36,398 images in this collection from April 2013 to till date. If I print L8 onto the console, it will give an error because of it is the number of elements is more than 5,000. After accumulating over 5,000 elements, it will abort. So we have this error now. And then let us comment it. Now next what we are doing is we are filtering the Landsat 8 image collection over the year 2000, like temporal filtration, like just as we have done in case of chirps, which was a single band image. Here it is multi-band image, but it is also an image collection. Chips was also an image collection. So I am applying the method filter date, and I am giving the start date and end date because we have already seen it. There is no need to repeat. Then we are printing the size of this collection. After now initial collection has around 11 lakh elements. Now let us see after this filtration how many elements will be there. Because it is not a daily data, there won't be 365 images in this collection. It is Landsat imagery are available after every 8 days or 16 days. So there are around 1,43,244 images, or because so many images are available for across the world. We haven't filtered it for the region of interest. So Landsat image, the Landsat path passes at the same point after every 8 days or 16 days. But across the world, there are so many images. Now further, if we go ahead and filter the Landsat 8 image collection or the region of interest, which is a point of interest, which is a point, what happens is it will filter all those Landsat images for the year from the collection from the year 2020, which are intersecting with this point, So sometimes the Landsat path may be going with the swath like this. Sometimes it may be going this way. This point may be on the edge, and sometimes it may be on the in the middle. So it will collect all those Landsat 8 images which are intersecting this point for the year 2020. So we are defining a variable L8 filtered, and we are taking input as L8 filtered over time, already filtered image collection, which has 14,000 1,43,244 images, and we are filtering for that region of interest with this method dot filter bounds ROI. You can search for that method to know to see the documentation and other details, like it is a shortcut to filter a collection, that is image collection, by intersection with geometry. Our geometry here is a point. Items in the collection with a footprint that fails to intersect the given geometry will be excluded. So it returns a collection. It takes a collection, it is applied on a collection, and it returns a collection which is L8 and I am printing the size of the L8 filtered temporally, after filtering temporally and spatially, and then let us see what will be the size of this collection. It is only 20, therefore there are only 20 images from around 11 lakhs we came down to 1,43,000, and then there are only 20 Landsat images for the year 2020 which are passing which are intersecting this point, then if we are adding this filtered collection to the map canvas, what it will show. It will so it is showing some image with lot of clouds. So by default, whenever we are printing a image collection on to the map canvas area, by default it will show the recent image. So it will show only one image, and it is also the visualization parameters. We are not passing any visualization parameters. We are keeping it as undefined, and we have named the list as L8 image collection, and this is a particular Landsat image which is intersecting that point of a region of interest. See, this is the image. This is actually the image collection, but on the top of it, what is being displayed is the last recent image in that collection, which has many clouds. So let us see how can we remove those clouds. Let us print this collection of 20 images onto the console and explore the metadata. So this image collection has 20 elements, and the latest image is from 1st December. This is in the format of 2020 year. 12 is the month and 101 is the date. So the latest image from 1st December 2020 is being displayed here. Now if we further see the properties of this image, the cloud cover is around 4.45%. So every image has this which is more than the cloud cover of this image which is from 15th November 2020. The cloud cover here is 1.14 percentage. So let us sort the this filtered image collection by cloud cover property from the metadata in the metadata and get the least cloud cover image. How can we get the least cloud cover image from this collection, filtered collection? We can define a variable where least cloud image is the filtered collection of Landsat L8 filtered, and then you apply a method of sort. You can uh, see the method sort under the Earth Engine image collection object class. It sorts a collection by specified property. What is the specified property? We are specifying it as cloud cover. So it will sort, and once it completes the sort by this property of cloud cover, we are selecting the first image among those 20 images. First image, it will sort in the ascending order. Um, uh, so the first image will be of least cloud cover. We can you can even examine this. Let us only sort the collection and print the collection. What we are doing is we are taking the Landsat filtered image collection, which was filtered temporally and spatially, and we are sorting it by cloud cover, and we are printing it. Once you sort it, it will only change the order, so it will remain it will have it will have the same 20 images, but in a different order. Let us run it. So it is printing an image collection. This first image collection is this one, L8 filtered, the original image collection, and this second image collection printed in the console is sorted one. And in the first image, let us explore what is the cloud cover. The cloud cover is 0, means there is absolutely no cloud cover for the first image. And in the last image, the cloud cover is 99.95%, almost covered. So if we are taking the first image, we are absolutely getting the least least cloud cover image. And if you run it again, so now this least cloud image is nothing but it is an image now, because we are only selecting the first image of that sorted collection. And if we add this onto the map canvas area, you can see this image collection is already printed, and now we are adding the least cloud color image. And there are no visible clouds on this layer, least cloud cover, and the layer below is a original image filtered image collection, and this is a particular image with least cloud cover. Then next we are Uh, Here we are trying to isolate an image from the filtered image collection. We are getting the first image from that filtered collection, and we are adding it. There is nothing significant here. I keep it commented. Now to display for proper visualization, you have seen in the first class about composite images, true color composite and false color composite. Now by default, in any image collection with multiple band images, Earth Engine selects first three bands and render as red, green and blue, and by default it will show, which is not a better visualization. Now to have a better visualized image, we have to um, we have to print a true color composite by assigning the bands which are in the same wavelength range, red part of the wavelength to red, and green part of the green to green, render it as green, and blue to render it as blue, so that it will the image will be the way our eye senses. So that you have already seen what you already know about what is a true color composite and what is a false color composite, so I am not explaining it. So let us run this by not taking the first image but by taking the least cloud image. So this is the least clouded image from the collection, which is printed as a true color composite by rendering the bands B4, B3, B2. Now what are these bands? Let us print information about bands in the image. By declaring the variable band names, we can simply see the Landsat collection description, where you have the names of the bands and the corresponding wavelength and description. You can see B4 is the red band with wavelength in the range 0.64 to 0.67 micrometer of the electromagnetic spectrum. Then B3 green in this range 0.53 to 0.59 micrometer of the electromagnetic spectrum, and B2 is the blue range, blue band in this range. So these are actually top of the atmosphere reflectance value, and reflectance in this band in this range of wavelength is collected by the sensor, and they are rendered. Red band is rendered, red region is rendered to the red color, green region is rendered to green color, and blue region is rendered to blue color. Then you will see a true composite. So that is what has happened here. Similarly, you can and, uh, and regarding the values of reflectance maximum and minimum value, you can see the range by customizing the range. The values are ranging between 0.06, custom stretching the range 0.06 to 0.16, so they are reasonable values. Then to render the image, this least cloud color image as a false color composite, the near infrared range, near infrared band is B5 in Landsat. So B5 will be rendered in red color. B4 red color will be rendered in green color. Red band will be rendered in green color, and green band will be rendered in blue color. So by choosing B5, B4 and B3 and in rendering it in the red color, green color and blue color, we will generate a false color composite. Let us run this script. So it is again generating all these layers, computing all those elements every time. So on the top layer is a false color composite. And you know why this false color composite is basically uh, used for studying the vegetation regions, which are vegetation is reflected, uh, has high reflectance in the near infrared range. So least reflectance is from the water bodies. If you custom stretch these, the values 100%, the values are ranging from 0.03 to 0.29. And if we apply the custom rendering, we custom stretch, we are having a better image, because earlier the values are being stretched only between the given minimum and maximum values, whereas the range is going outside in the especially in the near infrared range, near infrared band. So by custom stretching and applying it, you are having a better visualization. Now every time you need not pass on the visualization parameters, you can define a variable for visualization parameters for ease of use. Here we are defining a true color composite visualization parameters. Minimum we are defining a dictionary of visualization parameters with a minimum value of 0, maximum value of let us say we keep it the same 0.25, and bands B4, B3, B2 as in the case of true color composite, we are defining the visualization parameters, and then we can use it we can apply it to any image directly. Here what we are doing is we have done spatial reduction earlier. What in the we have in the previous script of single band image, we have used the reduce region method for spatial reduction for calculating the mean average slope and average annual rainfall for a region of interest. Now how to do temporal reduction? It is by using methods like median, mode, etc. Here what we are applying a temporal reducer. We are taking the original Landsat 8 filtered collection, filtered spatially and temporally, which has 20 images, and we are applying the method median. So for those 20 images, on each pixel it will have a value. then it will collect for each pixel, it will collect the median value of those 20 reflectance values, and it will generate a new image, a new median image. So we are declaring a median image, uh, um, and we are applying the median method on the filtered collection. It is in a way we are reducing the collection, image collection. We are aggregating the we are applying a temporal reducer, and we are collecting the median image, and we are displaying the median image on the map canvas area by using the visualization parameters just now declared, tcc underscore vig parameters, and giving a name of median image to it. Now let us see how it looks like by running the script. So again, all those images are getting displayed. First one, the original image filtered collection, then least cloud color image, then true composite of least cloud color image, and false color composite of least colored image, and now the median image. This is the median image now, which is in true color, and which is a true in the true color composite. The median image is again a single image. It has also because we are taking the median value for each pixel, it has also less least number, we cannot find much clouded pixels in the median image. So it is a very simpler way for removing the clouds. If there is too much of cloud cover, then we can apply this method of median temporal reduction to remove the clouds. Still there will be some clouded image pixels will be there. So either you can sort by the metadata using the cloud cover, or you can do this temporal reduction dot median, and there are better algorithms. Even there are Landsat specific algorithms for like for example, this ee.algorithms.landsat.simple cloud score, it computes a simple cloud likelihood score in the range of 0 to 100 using the combination of brightness, temperature, and normalized difference snow index. So what it does is by giving you by applying this method for a stack of Landsat images, it will calculate a cloud likelihood score in the range of 0 to 100 for each Landsat image, and it will add a band to each of the image, the cloud likelihood score. Now the one with the least likely cloud likelihood score will be the least cloudy image. So it is one of the ways for removing the cloud, or removing the cloud. We can, by selecting the low value, we can remove the clouds. So there are that is to say, there are there are many algorithms, other methods which are specific to Landsat, specific to Sentinel, which we can use for better visualization, for removal of clouds, etc. So that completes this script on working with multi-band image. We will now go to the next script. One more thing before going into the next script on computation of NDVI. Now, if we have seen that the median method removes clouds to a large extent, there are algorithms for compositing and removal of clouds. Now suppose if you have to download all the images of Landsat and prepare a composite, it will take many days, whereas as you have seen, we are able to create a relatively cloud free image in matter of seconds. So that is how Google Earth Engine is very useful for geospatial analysis. Now there is one thing, if we are running the script with if we are there is an option of just to have some idea about how the it runs on the server. You can run it with a profiler. You can run the script with profiler, which will activate a profiler tab on the right in the right panel. uh, it will it provides information about uh, the it will display a table of resource usage, like how much it displays information about the CPU time being consumed, the memory being consumed by specific algorithms, and parts of computation. Here, like you can see, these are the descriptions of each item. It is still being computed, and you can see the numbers are getting changed here. So how it the code editor is connecting to the server, and how it is passing on the information, and how much of resources are being utilized on the server. You can see it here, where here the compute is an indicator of CPU time taken by each of the operator. Peak memory is the maximum memory used by any single computation, and count is proportional to the number of times an operation was invoked. Operation mentioned in this description, like this is a encoding pixels to image is a description. It is an operation. It is it is invoked 135 times, and it has used a peak memory of 1.8 million, whatever units it is, and then it has this is 7.2944 is an indicator of the CPU time taken by the operation. Okay, just to give an idea. If you run it again, the profiler tab will be removed. So you can anytime you can run the script with this profiler to see. Let us say some script is taking a lot of time, and it is running very slow, or it is failing due to memory limit. Then to diagnose it, you can run it run with profiler, and then you can take corrective actions if the memory is being exceeded, or if if there is any error. You can see in the profiler where is the problem. Okay, then then the next script is on computing the NDVI, normalized difference vegetation index. From here on we will go faster, because we have already done the basics of importing the image collection, Landsat image collection. Here again I am importing, and again the same region of interest, I have taken a point. Then I am declaring the visualization parameters, minimum 0, maximum 0.3, and bands. I am rendering a true color composite by assigning B4, B3, B2 to red, green, and blue colors. Then I am filtering this image collection, Landsat image collection, over the region of interest, that is all the, and as well as over the year 2020 and region of interest. that is spatially and temporally and spatially. I am filtering the image collection. Then I am sorting the filtered image collection by cloud cover property, just as in the previous script. And to get the least cloud color cover image, um, I'm sorting the collection and then collecting the first image with the least cloud cover image. So IMG is an single image from the collection image collection. I am getting a single image which has least cloud cover. Now I will calculate the NDVI for this image, least cloud cover image, because the presence of clouds will distort the value of reflectance and therefore the NDVI value. Now NDVI, you have already learnt it in the first class. It is a normalized difference between reflectance in the NIR band and the red band. And why it is basically vegetation has higher reflectance in the NIR part in the and more absorb and least reflectance in the red part. Wherever there is photosynthetically active region, that is any region having vegetation cover, it will have high NDVI value. The range of NDVI will be between -1 to 1. So when the value is above 0.5 and close to 1, the vegetation, there is good amount of vegetation in that pixel. Um, that is there is it is a photosynthetically active region. So here what we are doing is, from the isolated image with the least cloud cover, we are selecting the B5 and B4 bands. B5 band in Landsat 8 is an NIR band, and B4 band is the red band. So we are assigning it to the variables NIR and red. Uh, we are selecting these bands and assigning them to these variables. Then we are calculating NDVI by using this expression. EE.image is the image Earth Engine container, and then this expression is making use of methods subtract, divide, and add. It is simple, NIR minus red divided by NIR plus red, and so it is calculating NDVI here. And there are because NDVI is so common, normalized normalized difference is so common, and there are so many indicators in um, for image analysis, remote sensing image analysis. We have a defined function of normalized difference in there is a method called normalized difference. We can directly use it without using the this method of using the expression. Here we are calculating the NDVI through expression, and this commented portion, it will calculate in one line by operating normalized difference method on the input image and by specifying the bands. In this way you can see the function here, the method. This normalized, it takes input as an image and it computes the normalized difference between two bands. In case the bands are not specified, they are optional. The parameters are optional. If we are not specified, it will use the first two bands. But here, because in the first two bands of Landsat are B1 and B2, we are not much interested, so we have to pass the specific bands for calculation of NDVI. So then we can also use user defined function to calculate NDVI for an image. So yesterday we have seen about the user defined functions, the utility of user defined functions. Um, Here we are defining a variable add NDVI, and we are using the keyword function to define an function. This function will take an input image, and with the input image inside the curly brackets, what it does is it will operate upon input image the normalized difference method, which is available in the Earth Engine image method, by taking B5 and B4, which are NIR and red bands. So it will this will calculate NDVI, and a new layer or a new image will be created. Here what we are doing is we are naming it as NDVI. Otherwise, by default, that new image or which has been created will take the first name of the first band, that is B5. So we are renaming it, and what we are doing is we are adding that calculated NDVI layer as a band to the input image. So to the input image we are appending the NDVI band. So this function is a user defined function which calculates NDVI for any given input image, and will add NDVI calculated NDVI as a band to the same input image, and it will return the input image with an additional band of NDVI. So this function will be more useful when we want to calculate, we want to add and calculate and add an NDVI band to a stack of images, a big image collection. For a single image, calculation of NDVI is better done through expression like this, or through this normalized difference method. There is no need to use a user defined function to define a function in so many lines and then applying on a single image. Single image is not an efficient way. However, we will see how to use this such user defined function for calculating an NDVI of a series of images. We will see afterwards. I am commenting this out. And next we are calculating NDVI with the same user defined function. How we are calling it? We are the name of the function is add NDVI, and we are sending the image, the least covered image as a argument, and we are the return value, which is an image with an added NDVI band, we are assigning it to image with NDVI variable. Anyway, we are not using the user defined function here. Now, however, just to verify whether it actually adds the band, let us see. Let us print the band names before and after. I will comment even this portion out, and I will add print band names before and after application of this user defined function. Variable band names before and print band defining the variable band names after. So here what I am doing is I have commented out this portion where we are calculating NDVI through expression or through the normalized difference method, and here we are I am printing out the band names of the image, the least cloud cover image, um, before applying this user defined function which adds the band NDVI to the input image. Now here I am operating the function, I am the calling function, and giving this least cloud cover image as an input, so it will generate an output with the additional band. So I have to print band names after, to just to verify whether it is adding a new band named NDVI. Let us run it. So you can see there are 12 bands initially, and there are after application of this function we have 13 bands. So there is an additional band, the list of bands, there is an additional band of NDVI added. So this function is working. Anyway, let's comment this out and uncomment calculation of NDVI using the expression. Then we want to display the input image and NDVI layer in the map panel. So this line is adding the input image with visualization parameters defined here, that is true color composite, and giving the name of the layer as input image, and in this line we are adding the NDVI layer which was calculated here using IMG as an input, with minimum and maximum values of 0, 0.7 and a palette of red and green. That means low values, 0 and less than 0 values of NDVI will be red, and values of 0.7 and more will be in green in color. So let us see how it looks like. So we are having two layers: input image, which is a true color composite of input image, which is the least cloud color image, and then on the top of it NDVI image. So all these green portions are forested regions. Light green portions are they are patches of forests, and dark red portion you can see all the water bodies which have least NDVI, 0 and just below 0. They are in red in color, and the maximum NDVI is where we have forest along the Western Ghats slopes of the Western Ghats. So we have forested regions, and some regions here, these are also ranges, mountain ranges, which have good vegetation cover. So let us have a better visualization of this NDVI by a custom palette. So here we are making a palette, a list of hexagonal strings, which varies from white color to green color, As I said, you can search for these. I have taken this palette from an example given under image on computation of normalized difference from computation of normalized difference from Modi's data. So I have taken the custom palette there and I am using it here. I am defining a variable NDVI palette and using these hexagonal strings. The minimum value is it is not, this is white, and the maximum value hexagonal string. You can use this. This is very handy, colorxr.com. You can search for it. It is dark green in color, dark black somewhat. Anyway, so this is the custom color. Let us run this and have a look on how NDVI layer will look like. This is the true color composite of the input image, and then NDVI to print the NDVI we have to add the layer of NDVI with the minimum and maximum value and the palette, custom palette, which we have defined it here, and we are renaming it as NDVI. So you can see you have this image where all water bodies which have least NDVI are in white in color, and the dark patches, dark green patches along the western Ghats and the ranges in the Deccan Plateau, they are very green, and even the coastal plains, they are greener, they are very green. So and the yellow portions, maybe they may be these may be even the vegetation, even the agricultural fields. Dark green may be the forested region, and in this region we may be having NDVI or photosynthetically active region in agricultural fields. Okay, then this is computation of NDVI using Landsat image collection. We can do the same for Modi's data. The following script is adopted from examples of normalized difference provided in the script manager for computing NDVI using Modi's surface reflectance. So in case of Landsat, this is a top of the atmosphere reflectance. Even there is surface reflectance data even in Landsat. Here this mod is MOD mod 09G8 product. It gives an estimate of surface spectral reflectance as it would be measured at ground level in the absence of atmospheric scattering or absorption. Now, because of atmospheric scattering or absorption, there will be a lot of different the noise. Because of the noise, the NDVI values which are actually measured by the sensor on the satellite, it is not actual value. So this is a modeled data by correcting the disturbance due to atmospheric scattering or absorption. And in this data you have these are the bands red named here the bands are named in this fashion: surface reflectance B01, B02, B04, B03, and the range of wavelength in the electromagnetic spectrum is also specified in the description. You can search for this data, MOD #09 GA. Modi's surface reflectance product, which has these bands. At 500 meter resolution and 500 meter and 1 kilometer resolution. The image collection ID is this. We have already imported it. Now here we are using the, without importing, we are using the Earth Engine constructor and image collection ID. We are using the same ID. Here we are loading the image collection, and then we are filtering the collection again in the same fashion we have done it in case of Landsat, spatially and temporally. And to isolate the recent available image, we want to isolate the latest available image in this MODIS data. So we are giving the date range as 1st January 2021 and 17 February 2021. We are filtering it temporally as well as spatially. The ROI is defined as earlier a point near National Water Academy. So we are filtering and we are printing the MODIS filtered data. Let us see what it prints. So this is printing this is executing this print statement, which is printing an image collection, a filtered image collection, which has 43 elements in January and February. In 1.5 months, there are 43 elements, 43 images. Starting from 1st January 2021, it is actually a daily image. So you can have a better, if you want to plot a daily NDVI plot for any point, you can use this data, MODIS data, instead of going for Landsat data. Then let us collect the copy of the latest. We want to isolate the latest available image, which can be seen here. It is from 13th February 2021. Copy of latest available MODIS image from the console, and assign it to a new image object variable. Here we are declaring this, we are defining a new variable MODIS underscore img, and we are assigning this image ID using the constructor ee.image. We are assigning this image, latest available image, and now we want to calculate NDVI for this image, latest image, using the normalized difference method. So we are taking we are operating normalized difference method on this MODIS underscore img image, and here we are passing on the bands, NIR band and red band. Here you have defined it in the description. NIR band is surface reflectance underscore B02 and red band is surface reflectance underscore B01. So we are passing it, and therefore it will calculate the normalized difference NDVI, and we are using the same custom palette and naming it as a variable NDVI, and we are centering the here in these lines we are centering the map at this point, and then we are displaying the input. We are adding the layers of input image and the NDVI, calculated NDVI, in these two lines. So let us execute with making use of this NDVI palette and naming it as NDVI layer, and first layer is we are naming it as MODIS bands 143. We are assigning the bands surface reflectance B01 to red, surface reflectance B04 to green, and surface reflectance B03 to blue. That is, we are actually making a true color composite here. The input image, we are making it as a true color composite, and then we are adding the NDVI. Let us run it and see how it looks like. We can decrease the zoom level to 8 and run it again. So this is the true color Modi's true color composite of Modi's image, recent image, and on the top of it the NDVI. The resolution here is less than the Landsat resolution, where it is 30 meters in land. In the case of Landsat, it is 500 meters. But here temporarily we have a daily image in here, and therefore you can get daily NDVI here. So you can see that the water bodies, the NDVI is the least, and we have these dark patches along the Western Ghats, and then agricultural fields are also there. For example, this is Ujjani Dam, which has a big the command, and it serves a big command in the downstream, and which you can see the green portion here, green, active portion, which is not dark green, which is a forested region. These are agricultural fields. So this way you can compute NDVI, and you can display NDVI and the map canvas area. Next we will go to the next script on mapping NDVI over time. In this script of mapping NDVI over time, because we have already seen computation of NDVI using Landsat 8 collection, I'm not going into the details. We are here quickly going to the script. Here we are in the first line, we are declaring the visualization parameters for using it in the script, and here we are setting the map center at a particular location and giving the zoom level of 10, and we are filtering the image collection. We have imported the image Landsat image collection, and we are filtering it over the year 2020 for 1 year, from January 1st 2020 to 31st December 2020, and that is temporal filtration we have done using the filter date method. Then we are defining a function to calculate NDVI for an image and add it as a band, as we have seen in the previous script. It is the same user defined function which takes any image, will calculate a normalized difference, and rename it as NDVI and add it as a additional band to the same image. So now the important part is mapping the user defined function or the filtered image collection to calculate NDVI and add it as a band. Now this NDVI, this filtered image collection or 2020, how many images are there? Let us print out. Let us print the filtered. We will see the number of images in this collection. Okay, sorry, because we are not filtering it spatially, it is getting accumulated over 5,000 images, and therefore it is aborting. You can also do We can define a region of interest, a point or a polygon, and we can filter it spatially also. But here it's let us go forward. Now we are mapping the function or the filtered image collection to calculate NDVI and add it as a band. Here we are passing we are operating the method map. You can search for map in the docs under image collection. Basically, this map is a method which map is a method which applies to all elements of an image collection. For example, this filtered is an image collection, and on of Landsat images filtered for over the year 2020, and here we are applying the map method and passing the function, user defined function add NDVI as an argument. That means what it will do is it will apply this function NDVI to every image in this image collection filtered. It will so this line will map user map the user defined function or the entire filtered image collection, and will calculate NDVI and will add it as a band. So there are because we haven't collected filtered it spatially, it will not print the whole image collection, because after accumulating over 5000 elements it will abort. However, the size of this new image collection with NDVI bands is 1,43,244. And if we run it again along with run with profiler, let us see how much of the um, um, re resources it is consuming. See, loading assets, like loading the Landsat images, it is performing this operation 1,49,494 times, and it is using a peak memory of 268 M, whatever that means. And the user defined function algorithm, it is using a peak memory of 128 M. These are huge numbers. So we and the count is also, you can see here the count is 1,49,494. So the same operation on your system will take many hours, days together, mapping the function or the entire image collection. So anyway, let us go forward and prepare the chart of NDVI over the time at any point of interest. Now what we have done is, let us remove this print statement, otherwise it will give the same error again and again. So what we are doing here is making use of these geometry tools and making use of the base map. I have selected some points, like I have selected one point in the water body and named it as water body. I have selected one point in a vegetated region and named it as forest. It may be a private forest, it is as it seems to be. Then but it is a vegetated region. Then similarly, I have created um, other geometries, like built up in the Pune city. I have selected the rooftop of a building as a built up region, and I have selected a point in the command of Ujjani Dam. This is Ujjani Dam on Bhima River. This is the river and this is the canal system emanating from the reservoir, and nearby the canal these are all fields, agricultural fields. So I have selected a agricultural point in the agricultural field. So for the purpose of charting NDVI over time at any point of interest. So I am making use of a method print ui.chart.image.series. You can search for it in your methods in the under the docs. For plotting any time series, you can use this method. It generates a chart from an image collection. So we have an image collection with NDVI as a band, and plots derived value of each band in a region across images, usually a time series. So we are passing an image collection as an input. For region, we have to declare the point of interest, and others are optional parameters. It will generate a user UI.chart. So here I am passing image collection with NDVI, and I am selecting the NDVI band. So I am actually passing only one band, and region of interest region, I can change it. Now given I have 4 points, I have defined 4 points of interest. So let us plot for each point how the NDVI series time series looks like for year 2020. For the forest, let us run it. So the chart, you can click on this icon to expand it. So this is the plot of NDVI. The y-axis is NDVI value, and this is the date range. You can actually change the labels and legends and you can make it a good looking chart with customization of charts, which you can look at it afterwards. So for the forested region, consistently NDVI is more than more than 0.4. So it is almost it should be almost a constant value. But however, these troughs, these are very low troughs, like 0.056, 0.111. These may be due to any cloud presence of any disturbance in the atmosphere layer, or for some other region this may not be the true NDVI, or it may be because it is from the monsoon region, it should not be like it is not a photosynthetically active region, because the region which we have selected is from a wooded it appears to be a wooded uh, forest. Or we can even go further up in the Western Ghats. We can take some other image and we can plot. We can simply select the point, you can drag it and place it you should not place it in a shadow region. Let us say this point, which appears to be a forest region. Now let us run it again. Again, the NDVI plot, you can see it is very high, 0.7. However, there is some mm, drastic drop in NDVI value for some reason during these August and September 2020. It may be because of the clouds color or some other region. Um, so anyway, it is but you have got some idea that NDVI is consistently high in forested region. You can download the this in the PNG form. You can save it, and you can after proper labeling you can use it for your in the preparation of reports. You can download it as CSV also. Comma separated values, you will have an Excel, you can have a file of with the values, actual values. Let us even let us see and download and see how it looks like. So this EE chart CSV is an NDVI chart for that particular point. And one more thing is this NDVI image is available after every 16 days, because it is a Landsat 8. It is using Landsat 8 image collection. At any particular point, the Landsat image is available after every 16 days. If we are using the MODIS, just in the previous script we have used MODIS data, which is a calculated model, we have estimated value of surface reflectance we are using. You can have a daily plot of NDVI, which may be which may give a better look. So after every 16 days you have an image, you have a value of NDVI at that particular point. These are some outliers. Definitely they are outliers for whatever region that has to be explored. Then if we plot the NDVI for the field which we have chosen it in the command area, naturally NDVI should not be very high, like in the case of forested regions 0.7. It is less, and it is also cyclical. At the harvest time it increases and then falls down, and again it increases. Then if you plot it for built up area where there is no greenery, there is no photosynthetical active region, maybe that particular pixel may be having some greenery, but the value of NDVI should be less. So for built up area, the plot of NDVI looks like somewhat like this. The maximum value is going up to 0.18 and the minimum is 0, so it is consistently very low as per expectation. Then the plot of NDVI for water body, it should be near 0 or just below 0. So here again the plot of NDVI is around it, the average value is around 0, just below 0, 0.05. It is varying between minus 0.3 to 0.15 over the water body. So this is how we can plot the values. Now if we are giving a better if we are using Modis data, we can have a daily plot of NDVI. If we are using before if you process the input image by removing the color cloud cover, etc., we can have a better estimate of NDVI. So any better value of NDVI. So going to the next, we will go to the last and final script, which is on downloading and exporting images. In our final script, uh, this is our final script. So here we are importing the SRTM DEM data as a variable, and we are also importing the asset with the Pune district shapefile, which I have shared, which I have uploaded in the assets, and I have shared as a public. Um, I have shared it publicly so that you can make use of it. So here in the first part of the script, we want to explore we want to export the image, that is the SRTM DEM image for a we want to clip it for a particular region of interest, and we want to export it and save it to drive. We want to save it to our Google Drive. So let us see how to do it. Um, Here we are defining a region of interest 1, which is an um, um, rectangle. We are using the this image geometry tool to draw a rectangle, and we for drawing a rectangle we have to specify the lowermost left hand corner and rightmost topmost right hand corner coordinates, the longitude and latitude of lower most left hand corner vertex, and longitude and latitude of uh, top rightmost corner. So I have randomly uh, by making use of this draw a rectangle tool, I have drawn a rectangle. I have assigned those values here using this constructor, Earth Engine constructor e.geometry.rectangle, and I have named the variable as region of interest 1, and then I am adding it to the map canvas as a layer. Let us see how it looks like. So this is the rectangle. So you can manually you can also by making use of this geometry tools, once you draw the rectangle, it will also be imported in the import section, the geometry. Alternatively, you can define it as in this way, in this fashion. Now these are normal statements: centering of object at the zoom level of 8. ROA1 is our region of interest. Now we are adding SRTM to the map canvas area with this color palette, minimum 0 value, maximum 1500, and we are naming the layer as SRTM. Okay, then we want to export the image specifying the region and scale using this method, export.image.to drive. So let us see what it is. search the method here, in under the export class, you have an method export.image.to drive, which it creates a batch task to export an image as a raster to drive. Tasks can be started from the task tab, uh, and these arguments are mutually exclusive: CRS, transform, scale, and dimensions. Now let us not go into the optional parameters. Let us provide an image to export, and then region of um, a linear ring or polygon or coordinates representing region to export. These may be specified as geometry objects or coordinates serialized as a string. And then the scale, the resolution in meters per pixel. If you don't provide the scale, it will take a default value of 1000. Now if you are not providing the native scale, what happens is it will if the scale is less than the native scale, it will resample, and so there will be many pixels and it may create an error. And if the scale is more than the native scale of the image, then it will aggregate anyway. It will calculate using the nearest neighborhood method, resampling or aggregating, but it is always better to give the native scale. Now here, because we are using the image as SRTM, which is 30 meter has a resolution, you can provide the scale as 30 and the region as ROI1, region of interest 1, which is this rectangle which we have defined. And you are giving a description of this in the form of a string: SRTM image export task. Let us run this script and see what happens. So it is creating a task here in the name SRTM image export. Let us run the task. If you click it run, it will open a dialog box, which here you can make changes. Actually, you can export an image to your drive or to cloud storage, or even export it to an asset. Here make sure that you have enough space in your Google Drive, and make sure that the region is small. You should not take a large region. You should not try to export image for a large region, otherwise it will generate errors. And if you are exporting it a large region, we have to change the scale accordingly. You should not be giving the scale of 30 meters if you are exporting it for a big region. So you run it. So it will start this is a long running task. We have seen in the introduction yesterday that the task tab is for long running task, and once you run it, it will keep running in the background. You can continue with the scripts. So it will export this SRTM DEM for that region of interest to the Google Drive. At any time you can cancel the if you don't want to run it, you can cancel it. And this it shows the time that has expended on the task. On the question mark, it gives the status. It is the status is running on the server. It started 49 seconds ago, and it is still the first attempt. Okay, let it run. I have already downloaded. I have ran the task earlier, and I have already downloaded, and now also it has again downloaded, and it must have exported to the Google Drive. Let us see it. So you can see that it has been exported to SRTM. It has been exported to Google Drive. You can download it and you can visualize it in a GIS software. I am leaving that portion. Then in the second part of the script, we are plotting a histogram of elevation. We are generating a histogram of elevation for Pune district. We have already have a shapefile of Pune district in the assets, and this portion of the script is generating a histogram using this method. You can search this method ui.chart.image.histogram, which will generate a chart from an image. The image here is SRTM DEM image. It computes and plots the histogram of values of the bands in the specified region of the image. Here again I am passing the parameters in the form of a JavaScript object with keys as the name of the parameters and values as the arguments. So here I am the image is SRTM, the region is ROI2, the region of interest 2, which is the Pune district shapefile, and the minimum bucket width is 200. It is related to the plot. We will see it when we execute it, and then the set we are giving it a title, histogram of elevation in Pune district in meters, and then we are printing the histogram. Now let us run it. So in the console you have this histogram of elevation in Pune district. So this bucket width is this. On the x-axis we have the elevation in meters, with the each width of each bucket is 200 meters, and then on the y-axis you have the frequency, the number of pixels having the elevation in this range from 0 to 200, this many pixels elevation count, and then 200 to 400. So most of the pixels are in the range of 600 to 800, and then 400 to 600 meters, and then 800 to 1000 meters. So this is a histogram of elevation of Pune district. You can download it as CSV or you can download it as PNG and save it on your system. And you have also added the layer of this we clipped the SRTM image to using the region of interest ROI2, and then we have specified the visualization parameters and gave it the value, gave it the name Pune underscore elevation, and to display the DEM for Pune district on the map canvas area. You can inspect the value of elevation using the inspector tab. So that concludes today's session on raster data analysis using Google Earth Engine. We started working with single band images. We have seen multi-band images. Then we have in every script we have explored many methods which are frequently used for image analysis in on Google Earth Engine. and you can continue working with these scripts. You can start exporting, uploading your region of interest in the assets, and calculate. You can start playing with various scripts. You can instead of taking Landsat image collection, you can take modis for plotting the NDVI. And then you can also go through these examples. You can modify these examples just as I have done in some scripts. You can modify those, and you can customize it, and you for your region, and you can start working to gain confidence and